Okay, so lesson 2 in the life cycle of a star. And in this lesson we're going to look in more detail about how a star is formed. So we know that in the center of every solar system there is a star, and in the center of our solar system that star is called the Sun. So we're going to look at how a star is formed and what happens during its lifetime and how it ends. And we're going to also see about how stars are responsible for creating the elements that exist in the universe. So the first task you needed to do was look at the picture that was on the starting slide, which was a picture of stars taken from the Hubble Space Telescope. And when I look at this picture, what I can see is there are stars of different brightness. And also the stars have different colors. So they have different colors, there are different brightness. And the other thing I notice is there's lots of stars. There's, well, I think it's there's an interesting idea that was first developed by a scientist thinking about, or a philosopher thinking about, what it would mean if the universe was infinite, if it spread out in every direction and it never changed and it was infinite in size. And what he concluded, and you can imagine this looking at the picture on that slide, no matter what direction you look in space, you would eventually see a star. If the universe was infinitely big, you would eventually see the star. So his thought was, if this was true, that the universe was infinitely large and nothing ever changed where the stars were, they weren't moving away from each other or towards each other, then when we look out into the night sky, what we would see is actually bright light everywhere rather than these individual stars. So we see this is not the case. So this is one argument that was initially made to say that the universe is not infinite, that it's finite in size. But a really impressive picture taken by the Space Telescope showing us how many different stars there are in one small patch of space and their different brightnesses and colours. The next thing you needed to think about is, why are stars not all white? You need, and I sort of made this hint saying, think about what happens if we heat up a metal. Okay, so we see in this picture, which is a picture of what's called the Sagittarius star field by the Hubble telescope, they have different colours, and I've suggested to you to think about the colours of metal. So what we find is that as metal is heated, it starts to glow. And it glows different colours. It starts by glowing red and then more yellowy and eventually becoming what we say is white hot. So white hot is a way of saying that something is incredibly hot. It's white hot. So let's take an example. So we're going to think about something like iron. And these are very rough numbers that I'm going to give you. So something like when we start to heat iron and it starts to glow red hot. So this is the red colour. That corresponds to a temperature of something around about 500 to 600 degrees, something like that. So it goes from 500 is just when it starts to go red, and then it goes, so this is a dull red colour. It's about say 700 degrees. So let's make it 700 degrees. Then if it's got a really bright red, what's called a cherry red colour, now we're more around about 1000 degrees. If it starts to appear orange, then we're up to around about 1200 degrees. And then if we have something like a bright white colour, here we're up to around about 1500 degrees, something like that, roughly. So what we see is it changes colour with temperature. So the color means that the star appears hotter. At least the surface of the star appears to be hotter if it's got a more white color. So it seems to be linked to temperature. Now, before you look at the next part and check your answers, you must make sure that you've looked at the video and you've checked the answers on there before you've looked at that video before you check your answers on this video. So what you should do is, if you haven't watched it, stop this video and go and watch this video that's linked to it. The link is given in your pack, and then come back to check your answers on here. So make sure you pause the video and you check your answers. Now, in the next part of this lesson, again, you had to watch a video, so make sure you've done that before checking your answers on here. And you're looking at the complete life cycle of a star that's the size of our sun. You need to make sure you filled in this, what's the name for each stage and a description of what's happening. So this is the life cycle of a star like our sun. The start, everything begins in a nebula. A nebula is this giant cloud of dust and gas. Most of this nebula is typically hydrogen. And what happens then is the gravity pulls all the pieces of dust and gas together. And as the matter is all squashed together, it becomes hotter to form the initial stage of the star, which is called the protostar. Eventually, what happens is there is something called nuclear fusion happens inside the star, which tries to push all the material of the star outwards, while the gravity is pushing inwards. It's like as if there's an explosion outwards happening at the same time as the material is being squashed inwards. And these two forces are balanced. So the star then stays in this part called the main sequence for a long period of time. So for example, our star has already been in this stage for 4 billion years and likely to stay in that stage for several billion years still. However, eventually the fuel runs out for the nuclear fusion and the star swells up to become a red giant, where it starts to use other fuels to fuse things like helium and some of the other elements. However, that eventually has a limited time, so the star will eventually become unstable and it ejects outwards the outer layer of dust and gas, and that leaves behind this hot solid core, which is called a white dwarf. But there's no longer any reactions happening, so this white dwarf will just cool down and eventually become dimmer and dimmer until it becomes a black dwarf. So make sure you've paused the video and you check your answers. Right, now in the next task you're doing a very similar life cycle, but this time you're looking at the life cycle of a star that's very much larger than our sun. Again, make sure you've watched the video before you check the answers. Right, so once again, make sure you pause this video so you can check your answers. Now, when we've got stars that are very much bigger than the sun, the first three stages are pretty much the same. We have a nebula, then the gas, gravity pulls the gas and dust particles together to form a protostar, and eventually with nuclear fusion pushing outwards and gravity pushing inwards, the star enters its main sequence, this long period of stable, where the star is stable. But however, in this case, because it's a much more massive star, when the hydrogen fuel runs out, the star swells even larger than a star the size of our sun to something called a red supergiant. But again, it has the red color because the surface of this is cooler. What happens then is the star then continues to fuse different elements together all the way up to creating the element iron. That's the heaviest element that can be created by a star. But eventually the star runs out of fuel as well, and it explodes outwards as a supernova, creating elements heavier than iron. Now, the supernova is a really cataclysmic explosion. So it's a huge event in space. To think about, this is the biggest explosion you could possibly see. Now remember, we said that the Sun was part of the Milky Way, and the Milky Way is this galaxy with billions of stars. Well, a supernova can be so bright that the light that we see from the supernova can be brighter than their entire galaxies typically for a few days. So there are things that can be seen from right across the universe. They're incredibly bright. They're incredibly massive explosions. And during this explosion, elements that are heavier than iron are formed during this explosion. Now, after the supernova, this cataclysmic explosion, that throws away the outer layers of dust and gas from the star. And what we're left with is a really dense core. And this core is known as a neutron star. Now, a neutron star is a very strange object. It's incredibly dense. And to get some idea of how dense this is, people often use the example of saying, if we had a tablespoon of the material that makes up a neutron star, it would weigh about the same as Mount Everest, roughly, well, 1 billion tons or something like that. Or another way of putting it is, if you were to stand on the surface of a neutron star, your weight, that is the force that pulls you downwards, would be roughly 10 billion times larger than it is on the Earth. However, it's not the strangest object, because if the star is large enough, then a black hole is formed as the core of this that's left over after the supernova. And this object has got such high density that even light itself can't escape from this object. So it appears as a black hole. One of the things that was mentioned earlier in the video, and has been mentioned in some of the videos that the links were in your pack, is about the formation of the elements. So we know that all the elements are shown on the periodic table, but what I said was that the nebula is pretty much usually made up from hydrogen, and yet we know that we've got this huge number of over 100 elements that we know that exist, although some of them have only been created in the lab. So how do we get these elements, given that in the nebula we generally start off from hydrogen? So these other elements, the elements that are heavier than hydrogen, are formed by this process of nuclear fusion that's happening inside stars. So we start with the hydrogen. The hydrogen's got one proton, and what happens is atoms of the hydrogen are fused together or joined together to give us helium. So we've got 2 protons in the hydrogen, and those hydrogens are joined together to give us helium, and then the helium starts to fuse. So the helium fuses with the hydrogen, or the 2 heliums fuse together to give us the heavier elements, lithium and beryllium, and so on, all the way up the periodic table until we get to iron. So essentially the first 2 rows, and then the first half of the 3rd row, well, if we count it as the first 3 rows, including the hydrogen and the helium. So the first 3 rows and half of the 4th row, this is formed in stars. So these are formed in stars through the nuclear fusion process in stars. So the elements that are larger than plutonium, so these are the ones above 94, all of these are produced in the lab. So those are made by humans. And then we have heavier elements that are heavier than the iron, like these ones, germanium, arsenic, selenium. These are produced by the supernova process. So we've got the elements produced by supernova.